Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled Binary Digits, Logic Levels, and Digital Waveforms. Like I said in a previous lecture, people think that digital means it's high-tech in nature. That is not necessarily the case. Think of, again, smoke or no smoke. With the combinations of smoke and no smoke, you can create incredibly complicated messages using a code, and that's exactly what binary data is. Binary is two states, high or low, smoke or no smoke. In our particular case, it's voltage levels. There exists voltage, there does not exist voltage, high or low. And those combinations of low voltages and high voltages, we can represent data in a coded format. Okay, so again, it's not necessarily high tech. It's smoke or no smoke. It's a dot or dash for Morse code. In our particular case, it's voltage. Okay, so there exist two possible states and only two possible states. That is what we're going to try to illustrate here using these graphs. Okay, there are certain levels of technology that is currently used for digital electronics. As I've previously alluded to, we are going to be using TTL logic, transistor to transistor logic. There was an advancement. That advancement was CMOS, complementary metal oxide semiconductor field effect transistor. Now we are advancing into our programmable logic devices, and the programmable logic device which we're going to be using is an FPGA, a field programmable gate array. So you can make a TTL compatible, CMOS compatible. All these are is just kind of different flavors of logic. You can have all sorts of crazy different flavors here, where I define a 0 as a certain voltage level in one flavor, and a different flavor may have a different voltage level for the same 0, and same thing for a high. Okay, for our TTL circuits, which we are going to be primarily using, we're going to kind of skip CMOS. It's the same thing, it's just different voltage levels. They behave slightly differently. So TTL, a 1 is defined as 5 volts. That is clearly a 1. A 0 volt is defined as a 0. Okay, in our ideal world, all 1s are exactly 5 volts. All 0s are exactly 0 volts. That is not what's going to happen in reality. Okay, there exists a range of acceptable values. Okay, for 1, there's a low level and a high level, and there exists a range for zeros. There are a low level and a high level. And again, for TTL, 5 volts is a 1. 0 volts is a 0. For CMOS, which is a different flavor, there is 3.3 volts for a 1 and 0 volts for a 0. And this is kind of what this graph over here is trying to illustrate. This is our 3.3 volt CMOS. Here's our 5 volt TTL. Don't memorize this graph. I'm just trying to show you there exists a certain range. So for TTL range, input, since that's the one we're going to use the most, I'm actually going to go over this one a little bit. What is the acceptable value for a 1? Okay, so there's this thing called VCC. That is kind of our supply voltage. That's 5 volts. Okay, that's obviously a 1. When it is, okay, for an input, an acceptable input goes down to 2 volts. So anything within this region for an input is a high or a 1. Okay, our input low acceptable range, let's use a different color for that, is this range here. Obviously 0 volts, that's definitely a low. What is our input? Up to 0.8 volts. So anything within this range is considered clearly a low or a 0. The question immediately comes to your mind, what is this no man's land here? That is called an invalid. There must be an invalid region, because think about this example right here. If there existed an overlap between a clear low and a clear high. Let's say I've defined my high to be from here to there, and I've defined my low to be from here to there. Value right here, definitely high. Value right here, definitely low. Value right here, I don't know whether I'm high or low, okay? So that little no man's land in between is essential to the functioning of digital logic. There is clearly a 0, there is clearly a 1, and there exists no other possibilities which are acceptable, okay? So there are also different standards for output. For an acceptable TTL output, obviously 5 volts, yep, and you're going to say 2.4 volts. That's your acceptable output there. And then, whoops, let's use a different color. 0.5 volts, 0 volts. So low, high. So there are 2 standards, one for the input, one for the output. Why is there 2 standards? Well, what this is allowing us is a little bit of noise margin here, okay? So if this output is feeding that guy's input there, we're making sure we are well within this guy's range, okay? So it's giving us that noise margin. There's a tinier noise margin right there, okay? One brief thing about the CMOS too, you don't always have to supply it with 3.3 volts. You can actually supply it with substantially higher voltage, and provided it's capable of accepting that. I think it's up to 18 volts. I know it's 15 volts, but you might be able to supply certain CMOS circuits with up to 18 volts. But what you do is you significantly expand the region between high and low. TTL, you can't do that. You have to keep that supply voltage right there, 5.25 volts down to 4.75 volts. So it's got a narrower range for the supply voltage, whereas CMOS, you can expand that range. Okay, it's not just limited to 5 volts and 3.3 volts. They're exceedingly small values. 1.8 volts is considered a high. 1.2 volts is considered a high. Those are as a high. Those are considered low voltage digital electronic circuits. The one we're going to use, TTL, 5 volts high, 0 volts low. There exists a range of acceptable values, and there must occur an invalid no man's region in between, okay? Because we are existing only 2 states, binary. Bi meaning 2. Okay, so there exists 0, there exists 1. Okay, so we've talked about binary digits, acceptable logic levels, and now let's talk about digital waveforms. Okay, so what a digital waveform is basically voltage can take different values as time progresses. When they're combined in a usable format, that digital data is a code, and it can be used to represent data like I don't know, like wind speed or temperature or pressure or whatever, okay? So let's talk about ideal versus non-ideal. Our first example is an ideal waveform right here. It is clearly a 0, and at time 1 second, it instantly transitions from a 0 to a clear 1. At time 2 seconds, it instantly transitions from a clear 1 to a clear 0. If again we are using TTL logic, it's instantly 5 volts, excuse me, instantly 0 volts, instantly 5 volts, instantly back to 0 volts. We do not live in an ideal world. There are transition times that occur, okay? So what we're doing here in this second example, this is a non-ideal. Top one was an ideal. There exists a rising edge or a positive edge or a leading edge. So rising, positive, leading edge. And it takes a certain amount of time high to low, to go from an acceptable low to an acceptable high. And then it transitions for this time period here. And then there is a time that it takes to go from an acceptable high to an acceptable low. Okay, and that is time LH, time low to high. Okay, so what we're going to try to do is we're going to try to minimize the time it takes to rush across that no man's land. So in an ideal world, we want to instantaneously change from 0 to 1. In reality, there is a little bit of time that's going to hand it out in that invalid, unacceptable region. Our job is to minimize that. Okay, so let me go ahead and draw another graph here real quick. So consider, for example, a graph of the voltage across a charging capacitor. You know, it's charging up, discharging, and what we want to do is go ahead and, okay, from here to there, it is definitely a low. From here to here, it is definitely a high. This brief moment in time, unknown, invalid. From there, it is definitely a 0. This brief moment in time, invalid. Okay, the idea is to get those rising edges and falling edges to quickly and clearly transition from a 1 to a 0 and a 0 to a 1, so you're spending less time in the invalid region. You want to avoid those slowly creeping charging capacitors. There is this concept of periodicity and non-periodicity. Okay, if we look at example 1, that is a periodic waveform. Example 2 is a non-periodic waveform. The principal difference between these two is a periodic waveform. It is regular in nature, it repeats itself. It's what's known as a clock. It's constantly going over and over. Whereas the non-periodic, it seems to be random in nature. There is no naturally occurring repetitiveness to it. What that is, that's actually data. It's taking wind speed data. The wind is randomly going up and down. It's taking temperature data. The temperature is randomly going up and down. It's conveying information like music. It's not repetitive in nature, unless it's REM. That's really repetitive. It's conveying information. You can't really assign some of the quantities we're about to discuss to a non-periodic waveform. But there are something you can use, some data you can provide about clocks or periodic waveform. Principally, the period, frequency, and duty cycle. Okay, you should be intimately familiar with period and frequency. Duty cycle might be something you may have not have heard of it. We're going to go over each one of these things as a refresher. Period is the time it takes for a wave to repeat itself. So if I start here, and what I'm looking for, it goes 0, 1, back to 0. Okay? That is the period of the whole waveform. It is repeating itself. Do I always have to start at a 0? No. Let's start at the time it becomes a 1. It's a 1, then it's a 0. That same period, if it's truly repetitive in nature, is the same period there. Wherever you want to start, I don't care. I start on 0 because that's what I do, okay? So the time period is the time it takes to repeat itself. The frequency is the number of cycles per second, okay? So it takes 1 second to complete a cycle. How many cycles per second? 1 cycle per second, okay? If it takes a half a second to complete a cycle, how many cycles will it complete in 1 second? 2 cycles, okay? So there exists a relationship. Frequency, the number of cycles per second, is 1 over the period. The period is 1 over the frequency. You should remember this from from electronics 1, 2, and 3. And for some reason, every year I teach this class, people go insane and they totally forget what they've learned in electronics 1, 2, and 3. And I'm telling you guys, you got to know this. You got to know this for the first lab. And guess what? I'm going to quiz you guys on the first day you walk in. I'm going to quiz you guys about period, frequency, and duty cycle. So know it, figure it out, learn it now. Okay, for our example here, our periodic waveform, let me redraw this. Okay, so here's an example of a waveform that it looks like it's repeating itself roughly every 16.6 milliseconds. From here to there, 16.67 milliseconds. From here to there, 16.67 milliseconds. From here to there, 16.6 milliseconds. However you want to look at this thing, you're constantly repeating yourself every 16.6 milliseconds. So if the period is 16.6 milliseconds, what is the frequency? Go ahead, and this is what I'm talking about, actively participating in these lectures. Pause this thing and do the calculations, because guess what I'm going to do? I'm going to do the calculations right here and show you what you're coming up with, what you should be coming up with. Okay, so my frequency is 1 over t. How many cycles per second? If it takes me 16.67 milliseconds to complete one cycle, I should get roughly 60 hertz. Does that sound familiar? To those of you living in the United States, that is the common distribution frequency for AC voltage. Something we may not have discussed in electronics 1, 2, and 3 is this concept of duty cycle. If you could think about duty cycle as the time the pulse is actually there compared to the time it takes to repeat itself. Okay, so that's what's known as, you take, I'm going to call it little t, basically pulse width over the whole period t. So how we define the pulse width typically is from 50% of its high value, so 50% of its high value to 50% of its high value. That is the pulse width t. And by the way, too, time high to low is sometimes defined as 0.1 to 0.9, not completely from 0 to 5. Okay, so that's what our pulse width is. So for our example, our duty cycle, and it's typically expressed as a percentage. Okay, our duty cycle here for example 1, let's say the pulse is actually there for 8.3 milliseconds. So if the pulse is actually there for 8.3 milliseconds of every 16.6 milliseconds, what is our duty cycle? 50%. It's actually showing up only half the time. Does that make sense? Let's try a different example. Okay, so in the second example, what I've got is a waveform that is exhibiting slightly different visual characteristics. Okay, so let's pretend that that full period, which I've just defined there, is also 16.6 milliseconds. What is the frequency of example 2? The frequency is 60 hertz. Some of you guys might be saying, wait a second, there's something wrong here. The first one's 60 hertz and the second one is 60 hertz? Yes, because it's repeating itself every 16.6 milliseconds. The difference between 1 and 2 is what's known as the duty cycle. Obviously, the waveform number 2, the pulse is not there as much as it is in example 1. As a matter of fact, it's only showing up a quarter of the time because I'm going to define that pulse width there as 4.15 milliseconds. If you could think about that, it's showing up for one block, then it's not there for block 2, 3, and 4. Showing up a quarter of the time. So one would stand a conjecture that the duty cycle is 25%. Let's see if that's true. Okay, the duty cycle for wave 2 is the pulse width, 4.15 milliseconds, divided by the period, 16.6 milliseconds, times 100%. What do you get? Oh my gosh, 25% duty cycle. Because the concept of duty cycle is very, very important to your understanding of a lot of electronics outside of digital electronics. Think about the pulse width modulation, PWM, of a DC motor. If the if the speed of a DC motor is proportional to the voltage applied to it, what I can do is give it I can give it full on DC, and it's going to go at 100% of speed. And maybe I want to slow it down. What do? I give it pulses of 50%. Basically I'm giving it waveform 1. And what it does, it slows its speed down to 50% because it's proportional, it's linear proportional. As I increase the voltage, my speed, N RPMs, goes up in proportion to that. If I'm at 100% voltage, i.e. full on, I'm going at full speed. If I'm at 50% of the voltage, I'm half speed. If I'm at example 2, I'm at 25% of the speed. Buck chopper. Think about a buck chopper, which you'll probably be going over in semiconductor devices and circuits or power electronics 1. You are cutting the voltage down, varying the duty cycle. Okay, let's do one more example of this one. So here's the third example of a digital waveform. What we've got, it's going from 0 volts to 5 volts over the course of time. And what it looks like, we've got a periodic waveform because it's repeating itself every, let's say that's 20 milliseconds. So what is the period, the frequency, and duty cycle of this guy if it's on for 15 milliseconds? So first example, first answer, obviously the period, 20 milliseconds. What's the frequency? 1 over 20 milliseconds, 50 hertz. Does this make sense? If 16.67 milliseconds was 60 hertz, okay, so it's going faster, its frequency, the number of cycles per second, is higher. So for example 3 though, 20 milliseconds, it takes longer to complete its full cycle. Is the frequency faster or slower? It's slower, okay? So number of cycles it can complete in 1 second is slower. So always check your work. Does it make sense? If I increase the period, my frequency will go down. If I increase the frequency, my period will go down, okay, because of that inverse relationship. Okay, so it makes sense. Number 3, what is the duty cycle of this guy? Okay, if it's the pulse is actually there for every 15 milliseconds of 20 milliseconds, 15 milliseconds over 20 milliseconds times our percentage expression, it's 75%. So if we hook this thing to a DC motor, it would be going at 75% of the speed. So here's an example. What is the period for something with a frequency of 1 megahertz? And some of you guys might be already thrown for a loop because I gave you the frequency. I'm looking for the period now. Okay, so you got to be able to pop back and forth between these guys. So what is frequency is 1 over t. Obviously, t is 1 over f. So 1 over 1 megahertz, remember, 1 times 10 to the 6th. You got to remember your SI prefixes. What we should be getting should be 1 microsecond. That is our period. Okay, what is the duty cycle of this thing? If our pulse width, it's actually only there for 800 nanoseconds. Again, remember those prefixes. Okay, what is a microsecond, by the way? 1 times 10 to the negative 6th. What's a nanosecond? 800 times 10 to the negative 9th seconds. If you could think about this, 1 microsecond, it's 1,000 nanoseconds. If the pulse width is actually there for only 800 nanoseconds of 1,000, 800 divided by 1,000 times 100%, keep our units in there, what do we get? It should be a duty cycle of 80%. What I'm trying to illustrate here is your ability to flip-flop back and forth between these guys and do some unit conversions. Okay, if your calculator is set up correctly using SI engineering notation, should be no problem. Okay, your ability to carry those things forward that you learned in electronics 1, 2, and 3 is absolutely critical for this class and any second year class that you take dealing with electronics. Okay, the next thing I'd like to introduce in this particular lecture is something very critical to your understanding of later concepts of digital electronics, and that is what's known as the timing diagram. Timing diagrams, kind of like an oscilloscope. What they are is a time representation of a number of digital waveforms displayed on a graph. I mean, think about a multi-instrumental sheet music. What you're trying to do is figure out who's playing what at a specific time. Okay, so what you're going to display is signal A in red and signal B in blue with relation to each other. Okay, at what time, at a specific time, what is the value of A compared to the value of B, and vice versa. Okay, and how you do that is the use of what's known as a clock. Okay, the clocks are very, very important to digital systems, and they'll become especially important in sequential logic systems, which we'll be going over later. They determine basically they coordinate the activities of the system. They synchronize everybody going together. Okay, so if I define the clock's positive edge, i.e. its rising edge, as the time when data is sampled, what are the values of A and B with relation to each other? So there's positive edge 1, 2, 3, 4, and 5. So at positive edge 1, what value does A take? A 1. What value does B take? A 0. Positive edge 2, A is a 0, B is a 0. Positive edge 3, A is a 1, B is a 1. Positive edge 4, A is defined as a 0, B is defined as a 1. Positive edge 5, A is a 1, B is a 1. Okay, so what the clock is doing is basically it's synchronizing the activity. When am I going to read the data? Because I can't be following all the time. Okay, so you've got to define at times which you sample the data. So now, what would happen if my clock was going twice as fast? I've upped the frequency. Before I draw this thing, is my period going to go smaller or bigger? Think about it. And the answer is smaller. My period has gotten substantially smaller. Well, it's cut in half because I doubled the frequency. Okay, when do the positive edges occur there? Right there, right there, right there, right there, right there, so on and so forth. I'm just sampling it at a faster rate, okay? So for the example of B, I'm going to sample it there, there, there. Notice I've avoided that region right there. What I'm trying to illustrate here, you can run digital systems at extremely fast speeds, but not infinitely fast speeds, because if I double the frequency again, I might be sampling on that rising edge within the invalid region. So there exists limits, practical limits, at which the speed of digital systems go based upon the non-ideal rises and falls, okay? Because it might be in that invalid region the time you sample it, okay? So there are practical limits on data sheets, which we'll discuss, times that you, basically speeds that you cannot run these things at, okay? So what this thing is known as is sometimes known as a bit time, okay? It's sampled at a particular time, and it's going to stay that value 0 until it samples it again right there, so on and so forth, okay? We are not always limited to positive edges. We can additionally sample on negative edges. And this again becomes more important in sequential circuits, okay? But be aware that there are times to sample on positive edges or rising edges versus falling edges or negative edges, okay? One more thing I want to go over in this particular lecture is this ability to transfer data. Data is not going to be of any use to us if it's just sitting there. We've got to be able to transfer it. And there are two ways of doing that, namely serial, i.e. series. Think about series circuits in a line, or parallel circuits, kind of spread out, all happen at the same time. Okay, serial, as the name implies, stand in a line, and they're all trying to go into a door, into a single door. Parallel, 1, 2, 3, 4 pieces of data simultaneously entering 4 doors. Okay, what are the advantages and disadvantages? Serial, think about it. You're waiting in a line. Do you want to wait in line all day? No. If it takes 1 second for that dude to get whatever he's got to do, and 1 second for that guy to do it, 1 second for that guy to do it, and you're back here, how long does it take you to complete your task? 4 seconds. Okay, so that's a major disadvantage. What about parallel? If it takes 1 second for everybody to do whatever they got to do, all 4 of them simultaneously enter, takes 1 second. Okay, that's a pretty cool advantage about parallel versus serial. What's the disadvantage of parallel? You could have 4 wires. I mean, think about the hardware. Think about carrying large amounts of data. Think about a 4-bit system, 4 wires. 8-bit system, 8 wires, so on and so forth. 32-bit system, huge amount of hardware, your weight goes up. So that's an advantage of serial. So less wires. Disadvantage, longer. Advantage for parallel, faster. Disadvantage, hardware. Speaking of number of wires too, think about lab practices, guys. Your lab practices in digital electronics is a test of your organizational skills. The concepts we're going to discuss is not that hard. Honestly, all it is showing up to class, knocking out these lectures. It's super simple stuff. Staying organized, that's the challenge. How are you going to organize 8 bits? Think about ways to do that. Don't take the same color wire. Don't take 8 orange wires. Maybe you could take 8 orange wires and label them. Put A0, A1, A2, A3, A4, A5, A6, A7. Or even better, use resistor color code. Take different color wires. Think about what is 0, 1, 2, 3, so on and so forth in the resistor color code. Black, brown, red, orange, so on and so forth. Maybe use these wires. You'll know visually how those things work in a parallel system. Another thing is to write this down. When you're working on a circuit, take your pencil, not a pen, take your pencil, write it down. I have connected light blue wire from such and such to such and such. Have your lab partner write it down while you build the circuit. Write it down while your lab partner builds the circuit. Don't do this one. Don't have your lab partner built at one end of the circuit. and you try to build the other end and try to meet in the middle and somewhere in the plains of Kansas, it does not work like that. You guys are going to miss. One of you guys is going to mess up and it's not going to work. Okay, so staying organized especially as we get to more advanced circuits. And that's why we are going to definitely be discussing VHDL and programmable logic. It's enabling us to perform the synthesis and prototyping of pretty advanced digital electronic circuits without a lot of wiring mishaps, okay? So one last thing regarding serial and parallel, think about serials, those are your COM ports on your computer. I'm going to try to put in the applications of these things in the computer discussions because like I said earlier, some of our courses we were defined towards computer. It was very at the end. I want to start introducing some of these concepts as related to computer concepts earlier. Okay, so serial communication, that's a COM port or a mouse port, a USB port. What's the S in USB? Universal Serial Bus. Okay, parallel, LPT port. That's your printer port. That's your disk drive. Okay, when you take apart a computer or you drop it on the floor and gravity takes it apart for you, that's what that big old flat ribbon cable is. It's a parallel means of data transfer. Okay, this concludes this portion of the lecture. What we're going to do is do some example problems of timing diagrams and digital waveforms.